and welcome to Bay College's online lectures. Today we're going to look at section 8.2, part 1. That 8.2 deals with composite and inverse functions. This video will solely deal with the composite functions. So what is a composite function? Well, we know what a function is. If we have what we call our function machine, this is our function, I have an input. So I put in some value x into this function, and I get out my output, some value f of x. And we're familiar with the function notation. But what if I had to take this information from a function and apply it to a different function? Essentially what I'm going to do is I'm going to take the output of one function and use it as the input into a new function. Let's call this the g function. So f of x is my input. My output is g of, well, not x, because that's not my input, f of x. So we have g of f of x. Another way to write this, a different style of notation, is to say g of f of x. So there's, as we see in algebra, there's always two ways to represent, some notation. G of f of x or g of f of x. Don't let this confuse you. It's not a multiplicative dot. It means it's a composite function. All right, so you have those two styles of notation. Let's see where we actually have an application. Let's say we're working with temperatures, and I have a temperature in Fahrenheit, and I know how to convert it to Celsius. So this would be my function to convert Fahrenheit to Celsius. Celsius is a function of Fahrenheit. So C of f equals 5/9 times quantity Fahrenheit minus 32. But my end goal is to find out what the temperature is in Kelvin. Kelvin is another temperature scale. It's an absolute temperature scale. So we have two different functions here. But my goal is to have one input to get an output in Kelvin. So this is my goal. So what can I do here? Well, I can take my Kelvin function and I can evaluate it for my C function, where my input is actually F. So I want to, if I'm giving a temperature in Fahrenheit, my end result will be in Kelvin, my goal. Another way to write that is the Kelvin function composed of the Celsius function, which its input is f. So I evaluate it for f, and then I take this whole value and evaluate it in k. So what does that look like? Well, if I actually built this composite function, I would have 5/9 f minus 32. That is my inner function. And I put this whole function, the entire function, as my input into here. So in place of c, here's my c value. I put in this plus 273. Now I could distribute and combine like terms, but it's going to be an ugly fraction. But that's essentially the gist of a composite function. Now, if I want to know Kelvin, I plug in Fahrenheit, I subtract 32, I multiply it by 5/9 and add 273. So it's one mathematical representation to go from Fahrenheit straight to some temperature in degrees Kelvin. So let's look at building some composite functions. Here we have, we're going to let f of x equal x plus 4, and g of x equals x squared minus 4. And just for review, we can look at this and say, what's the domain of this? All real numbers. The domain of this, all real numbers. So we don't have any domain restrictions to worry about. Now, when we do the composite function, order does matter. F of g of x. That could also be written as f of g of x. They're actually read the same. They mean the same thing. Essentially what this says is take the whole function g of x and put it in for the function of f. So if my function of f is x plus 4, I need to plug g of x into it. That's what we see in these parentheses, the whole function, x squared minus 4. And then sometimes we have to do some simplification, and this one works out nice, x squared minus 4 plus 4. Well, these are just numbers, like terms. Negative 4 plus 4, no more number, 0. X squared is the composite function. Now, I did say that order does matter, so if I'm doing g of x, it's basically saying take the function f of x and plug it into g. So my function f of x is going to be plugged into g. Well, g is an x value squared minus 4. I'm evaluating it for the function f of x. Now here, there's a little bit of simplification we could do. We have to square this binomial, and we do that using FOIL. So we get x squared plus 8x plus 16 minus this 4. And we can see we have the like term of numbers, and I'm getting a little crowded here, but I'll put it here anyways. X squared plus 8x plus 12. This would be the composite function of g composed of f. All right, so hopefully we got that, and since it's a video, you can pause it, maybe write it down if you need to. I'm about to erase it. All right, now here, different notation, but it means the same thing. It says f of g of 2. Now, let's not worry about the f part for a moment. G of 2, if we're familiar with the notation, it says evaluate g for x being 2. Once you find that value, plug it into the whole function f. Well, since we've already found f of g of 2, of x, different notation, I can just take, instead of doing all this math, I can just take my composite function and evaluate this for 2. This is an intermediate step that you really don't need. It's just saying find this value and plug it in while we take the composite function and plug in that x value. Well, we know 2 squared is 4. Now, we can check that. What if I went to this here and I plugged into 2 squared is 4. 4 minus 4 is 0. Well, what happens if I plug 0 into this function? 0 plus 4 is 4, and that's what we got right here. So it does hold true. Now, order does matter, so let's evaluate this. G of f of 2. Well, let's evaluate the function f of 2 and plug that into g. That's what this is saying. Well, since we've already found g of f of x, and if we recall, it was, again, this is an intermediate step. You wouldn't have to write this down if you were actually doing the problems as homework. But I'm just showing you this is the composite function. I want to evaluate it for 2. Well, 2 squared is 4, and 2 times 8 is 16, plus 12. 4 plus 16 is 20, plus 12 is 32. Well, let's just make sure we did all of our math correct. Let's evaluate f of 2, just this piece. 2 plus 4 is 6. Let's plug that in to g, the outer function. 6 squared is 36. 36 minus 4 is, in fact, 32. So, by using a composite function, we can actually condense this into one mathematical expression and just do it with a single input. Instead of finding the input, plugging it in, finding the output, then using that as input into another function. You'll see a lot of this if you move on to statistics. Many of your formulas in statistics are composite functions. They're functions composed of other functions. Honestly, I believe you use this every day. You just don't think of it as a composite function. One example might be is your electric bill is $180, and you work for $10 an hour. Well, your pay is a function of hours. And your electric bill, well, that's a constant function depending on how much electricity you use. Let's say you use the same amount of electricity every month, and your bill's $180. Well, you could think of that as a composite function, and maybe you have before. You think, well, you know what? If I make $10 an hour, I have to work 18 hours every month just to pay that electric bill. That there is a composite function. You can say, my $180 electric bill cost me 18 hours of my work life. So that there is a composite function. We took our bill and put it in terms of hours. All right, let's look at an application problem here. And it's long, but we'll find out that the work isn't really that much. We just have to build a few functions. Now, our application problem is a store advertises a sale that takes off an additional 10% plus $5 off already reduced prices. And I'm sure we've heard that advertisement, already reduced prices. A sweater that costs X dollars is already marked has 20% off, find a composite function that represents the cost. So we want a single function that represents or incorporates both of these discounts. Now, we read the problem for the first time, so let's just make sure we understand the terminology. If we're talking about taking something off, we're talking about the discount. So that's how much we're not going to pay. But we want to find the cost, right? That's what this is. So we want to find out how much we're going to pay. So sometimes when we read it, just assess it. What am I looking for, right? And then the next statement says a sweater that costs X dollars is already marked as 20% off. Again, we have a discount. And then to build a composite function, we know that a composite function is built of at least more than one, because we're evaluating one function with another. So we need to build at least two functions. And with these two sentences, we can actually do that. The first function, since it is a discount, I'm going to change it up. If it's 10% off, I'm going to pay 90% of the cost. So I'm going to say, all right, we have a function of a sale price, and I'll say it S of X, because we were told in the problem to cost X dollars. So I'm going to let X represent my variable of dollars. The sale price in dollars is relative to me paying 90% or 0.9 of the cost of the item. And then I get an additional $5 off. So that off tells me I'm going to be discounted. Subtraction, I'm taking that away from that cost. So I just built the function. This is 10% off of the whole price. It's not 1x, it's 0.9x, 10% off. And then I'm going to take away an additional $5. $5 off that markdown price. So here's my function. What's my next function? Well, if we read the next sentence, it says a sweater that costs X dollars is already marked as 20% off. Well, I can build that function real easy. My, what do we want to label it as? My markdown price, we'll call it M of X. And you can choose your own function notation. You know, if you want to put rainbows in, that's cool too. So M of X, 20% off. I'm going to pay 80%, so 0.8 of the price that it is marked. So we're going to get this 20% discount. That's what that means. Now, we're ready to actually answer the question. We built two functions, one that for the one sale price, and then one for the reduced price. Maybe I should have called this R of X. It's already reduced 20%. So to build a composite function that represents the cost that I'm actually going to pay out of pocket, so I'm going to call this my cost function, C of X. This is my composite function. Well, if I have a sale price that takes off an additional 10% plus $5 off already reduced prices, well, what it's marked as, this is my reduced price, this is what it's additionally going to take off. So I'm going to evaluate this function with this function. So essentially S of M of X. That's what my final composite function is going to be. So let's do this. Let's do what we did in the previous examples. This is my inner function, 0.8x, and I'm going to replace that whole value in for this x. So I get 0.9 times my m of x, which is 0.8x, minus $5 more. And if we look at that, we can say, all right, there is some simplification we can do. 0.9 times 0.8 is 0.1 or 0.72x minus $5. So good news is we're actually going to pay 72%. Essentially, it's a 28% discount minus $5 more. So it's a pretty good deal depending on the sweater. I personally don't wear sweaters, but you know, it's a personal call, just like rainbows for variables, your choice. That's been 8.1, section 8.2, part 1. The next section, we're going to talk about inverse functions, and then we'll tie it all together using a composite function to check our inverses. Thank you for watching.